So in our first example, random sample of 200, pick that information out, write it down. We assign that to be the sample size. And the proportion has ever driven a car. Okay, so the proportion of those 200 from the sample that have ever driven a car while under the influence of alcohol was 0.37. So the 0.37 is from the sample, and we call that the sample proportion. If we were going to interpret it, we would say 30% of those surveyed claim that they've driven while under the influence of alcohol. We know that this is our, okay, so this is what we call the point estimate, and it's given by a formula, and that formula is x over n. So if we do have the p hat here, and we do have the n, so then we can use those two numbers to find the missing value of x. And if you remember that it's the x value that we plug into the calculator program and not the p hat value. So we know that p hat is 0.37, and we know that n is equal to 200. So if x over 200 is 0.37, if you take this equation and multiply by 200, you get x is equal to 200 times 0.37. And yeah, what is that? 74. So it must have been that in that survey, when they contacted 200 people, 74 of the 200 said, you know, yes, I've driven under the influence of alcohol. And then 74 divided by the 200 gives you the 0.37. All right. And I ask you to fill these out. And just to get you practice in identifying the critical value. So the critical value will be Z, and we actually calculated all these, so you can just go to that table from last time. If 80% is in the middle, then we have 20% outside the middle, and we have to split that into the two tails. And so 10% is in the right tail and 10% is in the left tail. And you can consult your table to find these critical values, but I'll just go ahead and calculate it. It's going to be using the inverse t, or the inverse norm function, and I think we can just put 0.10. If you put 0.90, you're really going to get the one that you want, which is the right one, the positive one. But if you just put in the 0.10, you're going to get the negative one. And this notation asks for the positive one. So we have 1.282 is what we'll estimate this to be. So that's a critical value. So you're going to get some more practice doing those, or at least linking those numbers up. The margin of error, we have lots of different ways we can calculate that, but I'm going to go right to the calculator function. And it starts in the stat menu. And then we're going to go over to tests, and then select the one prop Z in, option A. All right, so when you execute this function, it's going to ask for the x. And notice that in this problem, we were given n and p, and we were not given x. And that's why we had to calculate the x value of 0.74. So 74. So 74, n is 200. If you give x anything other than a whole number, it'll give you an error. Expects a whole number here. And the first row, we're going to be using a confidence level of 0.8. So I'll put 0.8 in for the C level, and then calculate. And this is the confidence interval right here. So this is what I'm going to enter in over here. You need a lower bound and an upper bound. Now, the last thing we need to do is to do the margin of error here. And the margin of error does come with a complicated formula, but you know, we're not going to probably use that here. Here's the formula for the confidence interval. It's the critical value times the standard error term. Okay, so maybe we'll look at this here in a second, but what I would recommend instead is to draw your confidence interval using those two numbers. We know that it's constructed, the confidence interval, so that p hat is in the middle. Then we add a little bit, subtract a little bit. This little bit that we're adding and subtracting is what we're looking for in this case, the margin of error. So if we take these endpoints, 0.32625 and 0.41375, here's the confidence interval. So I'll calculate it in 4 different ways, and we'll confirm that all 4 ways are the same. The margin of error, if you just take the 0.37 and subtract the 0.3265, you get the margin of error. So that's this minus this. If you take the upper bound, 0.41375, and subtract the 0.35, this minus this would also give you the margin of error. If you take the bounds, and let's suppose that you didn't even know that 0.37 was in the middle, you could calculate the margin of error by subtracting, doing the range here, and the range would give you 2 of those margin of errors, so you divide by 2 to get just 1 of them. Then finally, I'll go do this one up here just so we've already calculated the critical value, 1.282, but then we have to multiply by p hat, 0.37, and then q hat I didn't write here, but that's 1 minus p hat. So if you take 1 minus 0.37, you get 0.63, right? So 0.63 and then divide by 200. All right. You don't have to use all of these methods. I just want to once again illustrate the connection between all of these different ways. So let me just show you that indeed we get the same margin of error no matter what we try here. 0.37 minus 0.32625. And I'm just going to round to 3 decimal places because my critical value up here is rounded to 3 decimal places. So 0.044, 0.41375 minus 0.37, again 0.044, and then if we take 0.41375 and subtract 0.32625, we get this number, but then we divide by 2, and again 0.044. And then this one up here, 1.282 times the square root of 0.37 times 0.63, all divided by 200, and again 0.044. So no matter how you do it, the margin of error is 0.044. So that's what we're going to enter in right here. All right, well, complete this table and then answer these questions. So what you're seeing here is in this table, as the confidence level increases, goes from 0.80 down to 0.99, what's happening to the critical value? Is it increasing as you read down the table, or is it decreasing? What's happening to the margin of error? Is it increasing or is it decreasing? Or is it staying the same? What's happening to the confidence interval as you go down? Is it getting wider or is it shrinking as you go down the table? All right, so that looking at the numbers in this table will help you to answer those 3 questions there. So just circle the correct one, increases or decreases. Here's another problem here, but what I would like you to see here is notice that we're changing the sample size. As the researcher, this is one thing that you can control. You can control the sample size. You can also control your confidence level. So in this one, as the sample size increases, what happens to the margin of error? What happens to the confidence interval? And then I have you ask similar questions or answer some similar questions here. As the sample size increases, what happens to the margin of error? And what happens to the width of the confidence interval? And then finally, number 3 here, this is the one where you answer the question about the sample size. So I'll give you the sample size formula. Here it is. This is the one that we use for proportions. Here's that critical value again, and then there's the margin of error. And remember, we're going to round up to get the sample size. And repeat the problem if no previous result is known. In problem 2 up there, for this one right here, the sample proportion in number 2 was given to be 0.61. So p hat equals 0.61. And the C level is consistently 0.95 in this problem. And then the n is going to change here. So you might want to calculate, here's the n, the x in each case, because the x is now going to change. The p hat stays the same, but if the sample size increases, then the x will increase. So you're going to have to calculate the x in order to punch things into your calculator, because it's going to ask for x as the very first number. Increases, as we read down here, the margin of error, these numbers are also increases. As the confidence level increases, the critical values are also getting larger, increases. As the confidence interval increases, the width of the confidence interval. Now, if you wanted to check this out graphically, it's easier to see. And so let me just go to a picture. If you were to graph this confidence interval right here, the 80%, it would look like this. So I drew a scale up here so you could see where these numbers would go. 0.326 versus point. All right, so here's the width of the first one. Now, when you go to and graph the width of the next one, and the one after that, and the one after that, this is what those confidence intervals look like. So if you graph them on a uniform scale like this, you can see that as the confidence level increases, the width of the confidence intervals also increase. And here's the idea. If you want to be more confident that you've captured the true population proportion, and that's in fact what we're trying to do here, we're trying to estimate the population proportion. If you want to be more confident that you've captured the true population proportion, you should add more numbers, a wider interval. The wider the interval, the more confident that you've captured the true population proportion. So widens in this one. On the bottom, one thing I do want to caution you about is that we must check NPQ every single time. We don't have P and we're trying to estimate P and Q, so the best we'll use is, the best we have is the sample proportion. But you should have seen an error here when you tried to put in X as 12.2. And what it's telling you is that something's wrong. So if you ever get this, then you could use an estimate, use 12, and that's probably what it was, because it has to be a whole number. But you can't do it here because N times P times Q is less than 10. So if you check N is 20 and you multiply by 0.61 and then you multiply by 0.39, this number is less than 10. So you don't have a normal sampling distribution, so you can't use the procedures in this section. A one prop Z interval. It's not normal, so you can't use the Z distribution. So we just can't do this one. That's all. But you can do the others because N times P times Q in all of these other situations are larger than 10. You need to calculate the X using our sample proportion formula. And every time the sample size changes, the P hat's going to be 0.61. So if N changes, so will X have to change. And here are the different values of X. We write these down because these are the numbers that we have to put into the one prop Z int. Okay, I didn't see much, and these are decreases. You can see as the sample size increases, the margin of error decreases, and then if you drew these, you'd see that these are decreasing as well, these confidence intervals. As a researcher, you can control the sample size, you can control a little bit, you can control the confidence level. So if you need more accuracy, increase the sample size, accuracy in your estimate. And then here is the worked out solutions. You need to know this formula if you're looking for a sample size. How many should you sample? What should the sample size be? You're looking for N. And so we don't have a calculator function to determine this, so you're going to have to work this one out by hand. And here's the formula. It comes directly from the margin of error formula. We derived that last time. And if you have a previous estimate, like what we have in problem number 2, we'll use it. If we don't have a previous estimate, we're going to use P hat is equal to 0.5. And whenever you use 0.5, the estimated sample size is always going to be a little bit larger, sometimes a lot larger. And the other thing is that once you get these numbers, you want to round up. You need to round up to the next nearest whole number. If you use 571 instead of 570, your margin of error will be slightly less than 0.04, might be 0.0399 or something. We are now going to move to the next section, and we're going to be pretty much doing the same thing. You're going to have, we're going to be dealing with means, and so you're not going to use the one prop Z int anymore. You're going to use a confidence interval function for mean. If you have this inverse T function, and you can check, most of the TI-84s have it. It's going to be in the same menu where you see inverse norm. So let's go to that menu in the distribution menu, and here you'll see it option 4. So inverse norm is what we use to find the Z critical values. for confidence intervals for proportions. You're going to see today that the mean sampling distributions are not necessarily normal, but they fit more a student t distribution. And the t distribution is a family of distributions based on the sample size, or this thing we call degrees of freedom. So it's going to be this inverse t that works a lot like inverse norm that gives us our critical values. The older calculators do not have this function, and that's why there are instructions here to download the program in case you don't have it. So this is a 3-page document that comes with your graphing calculator. And you'll see today where we actually use that. Okay, I'm gonna go through a lecture now, and it's going to parallel what we've done in section 9.1. We're still gonna do the same things. We're gonna talk about what a point estimate is, a critical value. We're gonna look at ways to construct the confidence interval. We have a calculator function to construct the confidence interval. And we're going to ask the same question: what sample size must you have in order to achieve a certain margin of error? So we'll do the same thing. All right, so I might go through this in a little bit more detail, but the first thing that you need to know is that we are no longer going to use a z distribution. We're going to use, and moving forward, we're going to have a lot of other distributions. Today we see the t distribution. Later on, we're going to use the chi-squared distribution and the f distribution. But in this section, it turns out through experimentation that the normal sampling distribution is not what we want to use for the sampling distribution for the mean. Rather, we want to use a t distribution, and there's a whole family of t distributions, and each one has this input, this degrees of freedom, and the degrees of freedom is equal to n-1. So with every different sample size, you're going to get a different degrees of freedom, and then the degrees of freedom to find the critical value, you can go to the table and find it. All right, here is what we're going to call the, it's like a z-score, but for means. And if I just replace this t with a z, you can see we take the mean, the sample mean, subtract the mean of the means, and divide by the standard error term. So earlier it looked like this, and then we had some formulas for these two. The mean of the sample means is equal to the mean of the population, and the standard error of the sample means is equal to the standard deviation divided by the square root of the sample size. Now, it turns out that the z distribution is not the best sampling distribution to use here, and so we're going to be using the t distribution. But other than that, it looks very similar. The only other thing is that generally we don't know the population standard deviation. So what we're going to use instead is the sample standard deviation. So here's the formula that we're going to use. Now, here are the properties of this t distribution. By the way, it comes in a table like this, and all of these numbers here are critical values. So it's not just like the z distribution where we had one critical value for an 80% confidence interval. We had one critical value for a 95% confidence interval, and so on. Here we're going to have a whole family of critical values, and it's going to be based on, well, the right area as before, but it's also going to be based on the sample size, and the degrees of freedom is equal to n-1. If you want, you can label the columns here. We're probably not going to use these columns. We rarely would use these columns over here. For most of our confidence intervals, we're going to be looking these middle 6 columns here. Anything from like an 80% confidence interval to a 99% confidence interval. And so if the right area in the right tail is 0.10, then the area in the left tail would also be 0.10. 0.10 plus 0.10 is 0.20. So if you have 0.20 on the outside, then you've got 80% on the inside. So this column here corresponds to the 80% confidence level. This column here corresponds to the 90% confidence level, and so on. The t distribution looks very much bell-shaped, just like the z distribution, but it's a whole family of curves. And as the n gets larger, the distribution will approximate, will get closer and closer to the z distribution. So while it starts off for small sample sizes to be fairly, it's bell-shaped, but it's not normal. As n increases, the t distribution approaches the z distribution. And this was the whole idea about if n is larger than 30, then we have an approximately normal sampling distribution. You can see some of the same properties as a density curve. The t distribution is different for different degrees of freedom. The t distribution is centered at 0 and is symmetric about 0, just like the z distribution. The area under the curve is 1, so we call it a density curve. Half the area is to the right, half the area is to the left, just like the z distribution. This curve here stays above the horizontal scale, even if we go out to infinity or negative infinity, just like the z distribution. And it turns out that one of the key differences is that the area in the tail here is, for the same horizontal scale value here, the area in the tail is a little bit larger for a t distribution than for a z distribution. And then here was that statement: as n gets larger and larger and larger, the density curve t distribution gets close to the normal distribution. Okay, so the first thing we have to do is to recognize that we're using a different distribution and know how to interpret it. So here, the first problem down here is one where we're going to go find the critical values. So let's take a look at number 8. It says find the t value such that the area in the right tail is 0.02 with 19 degrees of freedom. All right, so for 8a here, it must have been that n was equal to 20, so that the degrees of freedom, which is always n minus 1, would be 20 minus 1, which is 19. So if the degrees of freedom is 19, then the sample size must have been 20. We have the area in the right tail to be 0.02. If you put the area in the left tail to also be 0.02 and you add those two together, you get 0.04. So this would be what we would use in a 96% confidence interval. And what we're after is to find the t value. That's this number right here. We're going to use the same notation that we used with the z critical values. If the area in the right is 0.02, we're going to call this t of 0.02. All right. I'm going to get out the table now and show you how to read this. First of all, you come down here to the degrees of freedom equal to 19. So there it is. And then you go across the top till you find the area in the right tail to be 0.02. And notice that I've written above this that corresponds to a 96% confidence interval. And then find out where the column and the row meet. And that number right there is going to be your critical value, or what they're asking for in this problem. Find the t value for which 0.02% or 0.02 is in the right tail. So 2.205 is the number we want there. So we have degrees of freedom. So use the t table. Degrees of freedom, 19. Right area is 0.02. Find out where those two match, and you get 2.205. All right, and I'm going to replicate this problem with inverse t. So I'm going to show you how to use the inverse t function on your calculator. And it's in the same place where you see inverse norm. So go to the distributions menu and over here 4. And I believe here you have to first give it again, the calculator uses left area. So if the right area is 0.02, then the left area then would have to be 1 minus 0.02 or 0.98. And then you always have to specify the degrees of freedom, because the degrees of freedom is different based on the sample size. And if you look at this 3-place decimal here and you look what the calculator gives you, you can see and this is the correct critical value to 10 decimal places. But if you round it to 3, you're going to get this. So the table gives you the critical value, or inverse t on your calculator gives you the critical value. but in some problems, we need to know that critical value. All right, let's try these others. And there's 3 others there, so go ahead and practice and write your answers in the chat. So B, so we're looking for numbers like this that you get from the table. So just say B and give the answer, C and give the answer, and D and give the answer in the chat. So you're looking for this critical value right here. Problem C, they ask you about, they give you some information about the left area. But remember, just like the Z distribution, the T distribution has 0 in the middle. So even though you're looking for this one here, you can use the process to find this one. And then these two by symmetry will be opposites of one another. So because they're saying the left area here, that number is going to be to the left of 0, which makes it negative. And the negative value it'll take on is the same thing as the positive value over on the other side. For this last one here, I don't know if this is going to change anything, but for a 95% confidence interval, we're looking for T of 0.025. Because if we have 95% in the middle, then we have 2 or 5% outside, but we have to split that 5% in the left and the right tail. So it's 0.025 that you want. Okay. Looks like all the answers listed there. Some of them are different, but let's take a look. In the first one, you want to find degrees of freedom, 32, and they tell you what this right area is here. So you want to find that column that corresponds to an 80% confidence interval, and then go down and find that number. So the degrees of freedom, down to 32. Okay, so it's in the chart. And then you go over to the 80%, 1.309. And good, that's the answer that you all got. All right, and just to confirm with the calculator, let's do the inverse T. And since the right area is 0.10, the left area would be 0.90. And then the degrees of freedom for this one would be 32. And so you can see you get the same number if you round to the 3rd decimal place. All right, so you know where we're going with this. And just quickly here, the last couple for this one, 0.05. So we're looking at a 90% confidence interval, 5% here, 5% here. That leaves 90% in the middle. So with respect to this one, if there's 5% of the area over here, then there's 95% over there, and that's why we must use 95. And then for this one, okay, degrees of freedom is 6. So you should find 1.94. Right. Some of you have plus, some of you have minus, but when we identify critical values, we're generally going to write the positive one. But this particular one asked for the left one, didn't it? Yeah. So we want the negative. So the calculator function on this one would be inverse norm 0.05, or inverse T of 0.05, and then the degrees of freedom would be 6. And you get this number here. And then finally, the last one, probably the trickiest one because they give you the confidence level. 95 in the middle, 5% on the outside, so you're going to have the left area is 0.02, and the degrees of freedom is 16. 0.975 would be the left area if the right area is 0.025, and then the degrees of freedom on this one is 16. So 2.12 is what you have here. And for those of you who got 1.746, you probably put 0.05 here instead of the 0.02.
How do you know that that's a positive number and it's not positive and negative?
Because of where it's positioned. 0 is here in the middle, and these numbers here are just, to the right of 0. All of these have to be positive. So if you're looking for the right one, you have to get a positive number. Up here, this one was to the left of 0, so all the numbers over here are negative. So if you're looking for this one, it has to be the negative version.
So even though it gave us just the 95% confidence, it's not looking for both the positive and negative. You're just going to always go with the positive number?
Well, let me see how it was asked. It just says find the critical value. And when they say find the critical value, we're generally going to report the positive one.
Okay. Thank you.
In our formula for confidence interval, we're going to have the plus or minus sign. So it's going to be worked in. So one of the things we did in the previous section was we found these Z critical values, and you'll know that we actually use them. And so it's important to be able to find them. And the most important difference in this section is that we're going to be using a t-distribution. So we have a table, a t-table, or we have the inverse t, instead of using the z-table or the inverse z, or inverse norm. Okay, the next thing we're going to do is we're going to look at the graphical representation of a confidence interval and try to figure out what the margin of error and the point estimate are. So let me start with number 14, and it asks us to determine the point estimate. All right, so the first thing, when we're estimating a mean, and the only mean that we're ever going to want to estimate is the population mean. The sample mean is what we find that varies depending upon the sample size we choose, and it can be, you know, anything close to the population mean. The point estimate, the number that we use to estimate the population mean, a single number, is the sample mean. And then the confidence interval is constructed in a way similar to the way we constructed a confidence interval for proportions. What goes in the middle? Well, in section 9.1, where we were estimating the population proportion, p hat went in the middle. That is, the point estimate went in the middle. In this case, the point estimate is x bar. So we're going to take x bar when we construct this confidence interval. It goes in the middle. We've got the lower bound and the upper bound, and those are determined by the margin of error. And this interval is symmetric, and so the upper bound is going to be the mean plus the margin of error, and the lower bound is going to be the mean minus the margin of error. Okay. Take a look at one of their examples. And the example is that the lower bound of the interval is 20 and the upper bound is 30. So this is what the interval looks like if you graph it. 20 on the lower end. So here are the two numbers that they're asking us to find. They want us to find this number right in the middle. This is the x bar. This is the point estimate. They gave us some easy numbers for this first example, so you might be able to just do this in your head. The other thing that they ask for is the margin of error. So the numbers are simple in this case, and so we can say that x bar, in general, if you just take the midpoint between the two endpoints, you'll get the number in the middle. And the number in the middle is the x bar, and this is what we're looking for in this case. And then the margin of error, you know, you can take, you know, the upper bound and subtract the mean if you want, or you can take the mean and subtract the lower bound. And we're just really looking at the distance between 25 and 30, the distance between 20 and 25. So here are the two numbers that they wanted, the point estimate and the margin of error. Okay, why don't you try 15? Same idea, but they give you the lower bound is 5 and the upper bound is 23. All right, so go ahead and put in the chat, x bar equals, and margin of error equals. If you don't know, just write your name in the chat. Yeah, Carissa, careful about the order of operations there. Okay, so it looks like you guys are on top of things. Okay, so we're slowly building up to the problems where we're actually going to calculate a confidence interval. So here it is. The alpha generally are going to be small numbers, so I haven't talked much about this notation. Alpha will have a more significant meaning later on. It's called the level of significance when we do hypothesis testing. But, you know, if you take alpha and divide by 2, you get 0.05 divided by 2, which is 0.025. This is basically gives you tells you what how to determine the critical value. So z of 0.025 is the critical value. If alpha is 0.05, then we have 1 minus 0.05, which is 0.95. If you multiply that by 100%, you get a 95%. So what they're trying to tell us here is that for small values of alpha, that leads to, there's a relationship between the C level and the alpha value. Take 1 minus alpha and you get the C value, the C level. And they're showing us how to calculate the confidence interval. So generally for this confidence interval, we have the sample statistic plus or minus the critical value times the standard error term, or an estimate of the standard error term. So for proportions, it was this. The sample statistic was the sample proportion, plus or minus. The critical value was the z of alpha over 2. The standard error term was square root of PQ over N. And since we didn't know what the population proportion is, we used P hat and Q hat underneath there. So this is how the confidence interval is formed. And when you put these two pieces together, that's the margin of error. So you have P plus the margin of error, P hat minus the margin of error, and that's how the confidence interval was formed. Today, we're going to be using the mean. So to estimate the mean, the sample statistic, this is the point, also the point estimate, sample statistic will be the X bar. The critical value that we use in this case is the T critical value, T of alpha over 2. And then the standard error term for a mean is different than the standard error term for the population proportion. And you might recall it's sigma divided by the square root of n, but we don't know sigma, so we're going to use the sample standard deviation divided by the square root of n. So here is the interval estimate. Point estimate, interval estimate. All right, let's go ahead and calculate one of these. And then, you know, as before, I'm eventually going to take you to the calculator function. And you can see the technology steps here as to how you find that. We'll get to that in a second. First thing I want to do is to take a look at a problem and then answer many of the different pieces here. Simple random sample of size n is drawn, the sample mean, X bar. Okay, so they give us the sample mean. And in this case, if they ask for the point estimate, that's what the sample mean is. And the sample standard deviation is 8.7. Our author uses S in the formulas, but the calculator will use SX. So you can use either one, S or SX. So if we were to construct a confidence interval, we don't have enough information right now. But what we do know is that right in the middle, we're going to have X bar. But we don't know the margin of error, and we don't have the rest of the information that we need in order to calculate the margin of error. All right, so let's read on. Okay, part A. So this is number 20, and then we'll do part A. In part A, it says that we want to construct a 90% confidence interval. So our C level is going to be 0.90 for the population mean if the sample size is 40. And they want the interval. So here's what we're going to do. We're going to take our formula, here it is, rewrite it and plug in all these numbers. And we're going to construct it by hand. So I'm going to write the confidence interval formula and plug in all the information that we know. Now the T critical value is the one thing that is going to be, you know, not just apparent in the problem. This is the critical value, and to find that critical value, you either have to go to the T table to find it, if possible, or you have to use inverse T. One of those two ways to find that number. All right, so let's work it down. This is called the, you know, paper and pencil, work it out by hand approach. The X bar was given to us in the problem to be 35.1. The T critical value, we'll find that in a second, but these two pieces of information were given. The S was given up here, 8.7, and then the N was given to us in part A to be 40. All right, we still need this critical value. All right, now since N is equal to 40, the degrees of freedom is always one less than that. So the degrees of freedom in this case would be 39. Now, it would be great if we had a row for 39 in our table. If so, great. The other thing is that since we're dealing with a 90% confidence interval, we're not going to put 90 in there for T of alpha over 2, but we're going to use that 90 and the table, or inverse T, to find the critical value. So if 90% is in the middle, then we have 10% outside, which puts 5% in each tail. So this critical value is T of 0.05. You can find it by going to the table. If you have a row 39, degrees of freedom, and then you go over to the 0.05. And this is what we call the table approach. Yeah, looks like we do have 39. Here it is. And we go over to the column corresponding to the 90% confidence interval. And that would be 5% in each tail. So I'm going to come down here till I see 39, and there it is, 1.685. One other thing I should mention now that we're on the table, if you go all the way down to the bottom, look at these numbers are approaching. They're getting closer and closer and closer and closer to this one. And this one is the Z critical value. So as the sample size increases, so will the degrees of freedom. And as the degrees of freedom increases, the sampling distribution goes from a T distribution to a Z distribution. So you can see when the sample size is 1,000, you get numbers that are almost identical, 3 decimal places. All right, but in this one, we want 1.685. We can confirm that by inverse T, where we have the left area is 0.95 and the degrees of freedom is equal to 39. This one will give us something much more precise, a lot more accuracy. So 9.95 and then 39, and you can compare it. By the way, those of you with the that don't have inverse T and are going to have to go download the program, and even if you do have inverse T, if you want to get comfortable transferring programs back and forth to your calculator, then you can download this program, and when you run it, you're going to go to the program, and you probably don't have any programs in your calculator right now, but if you downloaded this program, you would see it right there, inverse T, and then you'd hit enter. So it says program inverse T, and then execute the program. It's going to ask for the left area, 0.95, hit enter. Oops, I hit 0.9. Degrees of freedom, 39. And I'm going to try it again. 0.95 and 39, and it gives you the same thing as the built-in inverse T function. All right, we're ready to continue now, because now we have this critical value from the table or from the calculator to be the 1.685. All right, I'm going to continue down here, and I guess what I'll do is just go ahead and type it into the calculator. All right, so we have 35.1, and first time through I'm going to use the minus sign, minus, and then the 1.685, and hopefully all of this looks familiar as to what we did last time. We're going to take the 8.7 and divide by the square root of 40. Notice we're dividing by the square root of n and not 39, not the degrees of freedom. All right, so the lower bound is 32.78. I'll round it to 3 decimal places. We know right in the middle is 35.1. And now I'm going to recall this last thing I typed in, and the only thing I have to change about it is to change the minus sign to a plus sign, plus or minus. And when I use the plus sign, I get 37.41, and I'll call it 8, rounding to 3 decimal places. So the answer, 32.782, comma, 37.418. There is our interval. If we interpreted it, we would say we are 90% confident that the population mean is between 32.782 and 37.418. Again, we use an entire interval of numbers to estimate a single population mean. Okay, now the calculator function. All right, so I want to be able to give you these same numbers without having to find the critical value and then do all this number crunching. All right, here's the calculator function that you want. It's called T interval. Now, nowhere in this descriptive title do you see the word mean, but the only time we're ever going to use it is when we have a problem for means. All right, it's in the stat menu again. So hit the stat key, and you come up with these 3 menus. I mentioned last time that the rest of this semester we're going to be looking in this 3rd menu here. And you want to go down to, there's Z interval. We probably won't even use that here. And here's T interval. And notice what it asks for. Okay, now, you'll notice the difference right at the top. It says input. And it's like, where do I get the information? If you had raw numerical data entered into a list, then you would select the data option, and then you would tell it what list you have, the frequency, confidence level, and so on. We didn't enter any raw numerical data into L1. What we have instead are the summary statistics. So the option we want is the stats. And then we're just going to enter in the 4 numbers that we need. In this case, we need the sample mean, and that is 35.1. The sample standard deviation also given to us in this problem was the 8.7, and then the sample size is the 40. Our confidence level is a 90% confidence interval, so we'll enter in 0.90, and then the last thing you need to do is to calculate. And you should see that the 2 numbers that it calculates, it gives you the interval first, it gives you the point estimate second, and then it gives you the other 2 numbers that it needed in order to calculate this confidence interval. But you should see rounded to 3 decimal places is exactly what we calculated by hand here. Has to be the same. All right, you can see that they, the rest of this problem, they said, okay, what if we increase the sample size? If you did that, that would change the interval. How does it change the interval? So be thinking about these questions as you're going through these. And then after we did A, then, okay, what if we increase the confidence level from 90 to 98? Keep the sample size the same. What's going to change the interval? And we'll look at that as well. Now, the more interesting problems are the applications. So let's do the same thing here. These problems really are, 30 seconds long, minute long. Part of it is just reading the problem and picking out the relevant information. Once you have the relevant information, you get out your calculator program function, T interval, punch in all the right information, and then we'll interpret. So maybe we'll spend some time to interpret this one. Okay, some of you might remember MySpace. Used to be the old, I guess it was the old Facebook way back when, or Instagram or something. But it was a social media site that I don't think it's active anymore. Maybe it is. The mean time spent on MySpace per user per month in July of 2014 was, all right, so what they're giving us here is the mean. The mean amount of time spent was 171.0. They give us a sea level of 0.95 for the mean. Okay, says has a lower bound of 151.4 and an upper bound of 190.6. All right, well, this is not so interesting. All right, so we can calculate there's no sample size given here in this problem, so we can't use t-interval. But when it says, what does that mean? Let's just interpret this to mean that they want us to interpret this confidence interval. So just like we interpret confidence intervals in section 9.1 when we were estimating population proportions, we're going to require the same 3 things when we're interpreting confidence intervals for means. So here's how we would interpret that. We now have a context. So we're going to say we are 95% confident that, and recall that the first thing we need to state is the confidence level. So we can do it like this. We are, I am, however you want to say it. Confident that. All right, now we have to describe in words this population parameter that we're estimating. And in section 9.1, we always began the rest of this with the word proportion. But in this section, we're estimating a population mean. So we want to start off by saying the mean. We don't want to say the proportion, that would be wrong. We don't want to say the amount, that would be wrong. We want to specifically use the word mean because that's what we're estimating. And what are we estimating? The mean time spent on MySpace. So it's not so bad to estimate it here. You can go into more details if you want. Per user per month per user per month in July 2014. Right. So all of that second part was to define and describe in words the meaning of the parameter that we are estimating, in this case, the population mean. And then finally, you need to use the boundaries of the confidence interval, since that is what you are trying to estimate, is between 151.4 and 190.6 minutes. And we have everything we need in the interpretation. We stated the confidence level. We've described the population mean that we are estimating, and we gave the boundaries of our interval along with the appropriate unit. So we haven't narrowed it down dramatically, but we have narrowed it down a bit. Somewhere between 150 minutes, that's about what? 150 minutes, 2.5 hours? And this is about 3 hours and 10 minutes. So we kind of have an average. All right, so interpreting confidence intervals is something else that you're going to be asked to do here. All right, maybe I'll do a couple of additional problems and answer all the questions here. The one thing I want to make sure that I do for you today is to show you the parallel to determining the sample size to achieve a certain margin of error. Back in section 9.1, in fact, some of those problems you just tried, you were asked to find what the sample size should be so that your margin of error would be small enough. And they would give you what the margin of error would be. For this one, they start off with this margin of error formula. This is the part x bar plus or minus t of alpha over 2 times s over the square root of n. So that whole part is the margin of error. So we start by saying that the margin of error is equal to this, and then we solve for n. Again, I won't go through the algebra here. We did it last time with the sample proportion, but we're going to solve for n. And if you solve this formula algebraically for n, you get this guy. The only difference is that we have to use the z critical value instead of the t critical value, because we're looking for a sample size, and the sample size is based on, or the critical value, this t critical value here that appears up here, is based on the value of n, the size of the sample size. Remember how we got it. We go to the table and we have to know the degrees of freedom. Well, the degrees of freedom is based on n. Well, if we knew the critical value, then we would have to know the n. We don't know the n, that's what we're looking for. So what we do is we use that limiting value. If we don't know the n, we're going to use n at infinity. And so we're going to use the z critical value down here. And you can see these numbers get smaller and smaller and smaller, and we're going to round up. All right, so here's our example. Dr. Paul wants to estimate the mean serum HDL cholesterol of 20-year-olds, 20-year-old females. How many subjects? Okay, so here's the how many subjects. And when you see this, you want to say, okay, find n. Are needed to estimate the mean serum HDL cholesterol of 20-year-old females within 2 points. Okay, so within 2 points here, what they've given us is the margin of error to be 2. Now it's not 2% here because we're no longer in the proportion setting. We're in a mean setting. With 99% confidence, C level equals 0.99, assuming that S is equal to 13.4 on earlier studies. All right, so we'll first do the 99, and then they give us a part 2 of this problem where they say, well, what if the confidence level was 95% instead? All right, let's work through this one. We're going to start with our formula right here. You're going to square the fraction. That consists of taking the z critical value and multiplying it by the sample standard deviation, and then we divide by the margin of error. Plugging in all the numbers we know the margin of error is 2. We know the sample standard deviation was given to us in the problem to be 13.4, and the only other thing we need is the z critical value. Remember these values, the z critical values, they're, close to, for a 99% confidence interval. You have a table somewhere. The z critical value, this would be z of 0.005, is equal to 2.576. And we get this by inverse norm. You can use 0.005 or you can use 0.995. This number will give you the negative. This number will give you the positive version of that. So 2.576, and let's just go ahead and finish this one up by plugging it into the calculator. 2.576 times 13.4 divided by 2 squared, and this is about 297.8799846. So we're always going to round up, so 298. Sample size, we always need a whole number. Okay, that's good for today. We're out of time. I will do a couple more problems before uploading these notes, and you can get these after class and then the video later in the week.